Okay, welcome back everyone. Hope you had a good weekend. Today we're going to start talking about how we train this two-layer neural network. And the first thing we're going to talk about is a modification to gradient descent. So as we discussed back in Unit 6, when we do gradient descent, we have some cost function or loss function of some parameters theta. Usually we set that to be the negative log likelihood. And then we minimize that over the parameters to get our maximum likelihood estimate. And when we look at the details of that negative log likelihood, we have, so typically we write it like as a sum of elements over the training data. But here what I did is I also divided by n. And that doesn't really change the minimization if you have the 1 over n in there or not. But in this unit, it makes some of the math easier to imagine that there's a 1 over n there, which means that you can think of this as like an average over the training samples of this loss here. And we also know that we can, if we have a differentiable loss, we can use gradient descent. And that says that the new parameters equals the current parameters minus a small step size times the gradient evaluated at the current parameters. And if we plug in this expression for the gradient, then because the gradient is linear, we can move the gradient through the sum, and we get this expression here. So when you look at this expression, you can see that the computational effort required in this term basically scales with the number of training samples you have. So if you have a very large training set, then you have to compute a lot of these gradient terms to do gradient descent. And that's an issue because as we get further along in the class and we consider more sophisticated things like this neural network, our training data sets are going to get larger. And so that's sort of the issue here, is that this gradient computation, every single time we do one update of gradient descent could be really expensive. And then the other thing, if you think about how gradient descent works, you have some cost function like this, and maybe you start here, and you don't take a direct path to the cost function. You take many steps. And so if you think like for each one of these steps, is it really worthwhile to spend a lot of effort computing this term if maybe instead we could do some approximation? If we can approximate it in a much more efficient way, then we could, for example, take more steps with the same computational effort, or just have less computational effort overall. So that's the other thing to remember, is that gradient descent, it's not like we're trying to go directly to the optimum in one step and we're worried about not getting there exactly. It's like we might be overshooting, we might be just going in the wrong direction. So it's not really clear that it's worthwhile to spend a lot of time computing this. Okay, so with those two things in mind, what we're going to do to simplify this is we're going to use what are called mini batches. And a mini batch is just a random subset of your entire training data. So you could maybe imagine training data like this. You have in total n of these samples. Imagine that you shuffle them and then just take out a chunk. So that would be a mini batch. And whereas you might have thousands or millions of training samples, a mini batch, maybe you have like 100. So it's a relatively small number. So you randomly select a mini batch, that's the idea now. And then you compute the gradient using only a mini batch. So that's the idea we're proposing here. So just to look at the details, maybe establish some notation. So if we think about our training data, we can index it using samples 1 through n. And let's say we get some subset of those indices 1 through n. That subset of indices we'll call IT. And if you put some absolute value signs around that subset, that's how you denote the size of a subset. So we're saying that this size here might be, on the order of 100 or something. And actually, it doesn't need to be fixed. You can scratch that out. The size is not random. So you choose, I want to use like 100, and then you randomly select 100 elements from your total set of indices. Okay, so now that you have that subset, when you approximate your gradient, rather than using all n, as we did there, we're now going to use only the subset, the elements in that subset, and we're going to normalize by the size of the subset. So again, this is an average, but we're averaging these terms only over a small fraction of our data. And we'll give that the name GT. So that's our gradient approximation. It's not exactly the true gradient over here. Oops. It's not exactly this, right? Because we're not using all the samples. We're just using some small subset of samples. But maybe it's going to be good enough for us. And then finally, once we have that gradient approximation, we just do our regular gradient descent update like this using the gradient approximation. And this thing is called stochastic gradient descent. It's stochastic because it's random in the sense that the subsets are random. And so every time you run it, you don't really know what trajectory it's going to take because the gradients are random. Okay, so that's the idea behind stochastic gradient descent. Any questions? Yeah.
So in this method, does it sample the data randomly every time, or like the first 100, next 100, if there are 1,000 samples like that?
Yeah. I'll show you a slide. A couple slides later, we'll get into the details. But basically, what we're going to do is we're going to take our training data set and we're going to shuffle it once. And then we're going to take out the first 100, use those, then the next 100, use those, and so on until we go through all the samples once. And then we're going to reshuffle it and then start over. So that's what we'll do. Okay. Any other questions? Okay, so now we'd like to understand whether this is going to be a good approximation or, is it good in some sense? So we'd like to justify this idea. So basically what we can show is that this gradient approximation is correct on average, or you could say unbiased. And it goes like this. So if you take the expression for the gradient from here, and let's say you do an expectation, conditional expectation, or expectation given theta t. So I'm just going to take expectation of this over here. And we're going to do, to make the analysis a little bit easier, instead of summing only over indices I in our subset, we're going to sum over all indices in the training data, but then we're going to insert an indicator function. So this thing here equals 1 or 0. Those are the two options. It's 1 if I is in the subset or otherwise 0. Okay, so that's what this indicator does. So now you can see basically the full sum with that indicator is the same as this partial sum, right? Because anytime I is in the subset, then this turns into a 1. which is what's happening here. But if I is not in the subset, then this is not included in the sum, just like over here. Okay, is everybody with me on this indicator function? Is that making sense? Yes.
So is this expectation considered in all the subsets too? Like,
So this is going to be an expectation over everything random except for theta t. So basically, we're not, the training data, this is not random because I just have like x1, x2. Theta t is not random because we're conditioning on it. So the only thing left is it. So this subset is what's random. That's the thing we're taking the expectation over. Okay. So far we just basically transformed the expression above into here. And any questions on this part? Is everybody good with that? Oh, yeah.
Why is the expectation of 1 over the magnitude of IT and if we're taking a subset?
So this is just the size of the subset?
Right, but I'm saying, like on the second slide where we go.
Oh, we haven't talked about this yet. So I guess we're just talking about, so far we're just making sure there's no questions on this. Okay, and now, if there's not, now we can actually do the expectation. So, so let's imagine this thing. This is basically a random number, right? That's either 0 or 1. And it's random because it's evaluating. It's going to be 1 if I is in that subset or 0 otherwise. And I is also like just fixed. So imagine we're talking about I equals 1. So this is like, is 1 in the subset or not? And the subset is random. So if you think about it, like you're basically, constructing this random subset. It's just like uniformly at random out of all possible subsets. And you're asking, is sample 1 in there or not? Well, it really just depends on the size of that set you're constructing. So, at the end of the day, it's just going to be this, the size of the set divided by n is the average value of this, or the probability that I is in the set. Does that make sense? Let me give you an example. So let's say that I have random subsets that are half my training data set size. So I have a particular I that I'm considering. Perhaps it's I equals 1. So that's fixed. I want to know what happens at I equals 1. And I'm imagining random subsets that are half the size of my full training data. So basically for half the random subsets I create, they will include the sample 1, right? And then half of them won't include that sample 1. So the probability that the first sample is in the random subset is 1/2. So, I don't know, is this making sense? So it's like just imagine you're fixing an arbitrary I, it's 1 or any number you want, and then you're just imagining creating random subsets. Is I going to be in those subsets? And so it's just a matter of the size of the subsets you're creating. Should we discuss this more? Okay, let's maybe think about a very specific example. Maybe I have 4 samples. So n equals 4. And so, and let's say I'm interested to know, and I'm looking at I equals 1 again. So out of this, and let's finally say that the size of my subset is 2. So given these, 4 slots, how many different ways can I make subsets? Maybe we could think of them as binary numbers. So It's all right. So this subset includes those two samples, but does not include the first two. So that subset might be indicated by that. I could make another subset like that. I could make another one like that. Let's see. Maybe I could be more systematic about this. I'm just going to try to make all the different subsets I can. Oops. Okay, so like, let's say, I look at the, if I take the last sample, then there's 3 different ways I could take another sample, right?
The last one is extra. 6 possible.
Do I have a redundant? Oh yeah, I have a redundant one.
Second one.
Yeah, exactly. Okay, right, and then so that, or if I take this one, then there's 2 new ways that I could complete my subset of 2. And if I take this one, there's 1 new way. So basically, yeah, there's like, does it make sense that these are all the different subsets I can create? And now let's say I'm drawing these at random, and I want to know how many contain I equals 1. As you can see, half of them do. How many contain I equals 2? Again, half of them. How many contain I equals 3? Half of them, and so on. So there's just sort of an example of if you say, like, what's the probability that a given I is in one of these random subsets, it's really just going to be 1/2, because we're looking at subsets of size 2 out of a total of 4 samples. So you can kind of generalize this to, more subsets, of course, or more samples, of course, you start to get more and more possibilities, but hopefully you can see that this is going to continue. Okay. So at the end of the day, what I'm saying is that, like, when you look at the average value of, whether a subset is there or not, which is basically like the average value of those numbers, it's just going to be the size of the subset divided by n. So that's what we're going to get. And that size of the subset is going to cancel this, and basically going to give us 1 over n sum. And this actually, you can recognize this as our original gradient expression. So we're basically showing here that this guy, the average value of our approximate gradient, is the true gradient. So it's correct on average, unbiased. Okay. So is that making some more sense? Okay, any questions on that? Okay, so because the gradient is correct on average, then a lot of other nice things happen. You can look at the parameters, the new parameters given the old ones. You could look at how, what is their average value. So based on the gradient descent update, we just plug that in here. And again, we're holding this fixed. So that means that this is deterministic, for that expectation. And then finally, we have alpha t minus alpha t comes out, and then we have expected value this, which we just derived above as this. So that means that this is the true gradient descent parameter update, and this is, the average approximate one. So on average, our approximate new parameters equal the ones we would have gotten if we would have used the correct gradient from gradient descent. Okay, so another way of thinking about all this is you could say the difference between the approximate gradient and the true gradient is really some noise. We can call it epsilon. Think about it as like a gradient noise. And what we've shown above is that gradient noise is 0 on average. 0 mean gradient noise. So what happens is when you look at gradient descent, maybe you're starting here, you have this nice smooth convergence to the minima. In stochastic gradient descent, you have this gradient noise that means you wander around. Sometimes you might actually go backwards, but sometimes you go to the left, sometimes you go to the right. But on average, you're following this. So this is maybe a couple different trajectories of gradient descent to get here. But if you looked at an average over all the stochastic gradient descent trajectories, it actually look like the true one. So that's what we're saying about this stochastic gradient descent, is that it's like a noisy approach. It like wanders around as you're doing gradient descent, but on average, it's moving in the right direction. Does that idea make sense? Okay. And if you don't like all that wandering around so much, what you can do is you can reduce your step size, your learning rate, alpha t. Essentially what that does is, it's kind of like, I don't know, if you've taken signal processing courses and you have like an autoregressive one or IR filter, it's sort of like that. Or in control, it's like you have this feedback loop. Basically, you average the old gradient approximations more and more, you reduce some of that noise, and what happens is you move slower. You move slower because your learning rate is smaller, but there's less bouncing around. So that's a sort of trade-off. And the smaller your batch size, the more stochastic your trajectory is, the more random it is, and generally speaking, you want to use a smaller step size to balance that. So this step size is something people choose together with the batch size to work well together. Because the gradient is so much cheaper to compute, you're not so much worried that when you reduce the step size, you have more iterations to take, because every iteration is just so much cheaper. Okay, so that's sort of the theoretical justification for gradient descent. Is that making sense? Any questions on that? Okay. All right, so then just a few details. So let's say we have n samples in our training data set, and let's say that we decide to use b samples in each mini batch. Typically, that's just a fixed number, like I said, maybe 100 or something like that. And then, essentially, you might ask, well, how many different mini batches will I need to cover all my training samples? So that's going to be n divided by b, but maybe n is not perfectly divisible by b, so you're going to have to round up. So that's what these ceiling operators are for. And so it could be that very last mini batch will not have a full B samples. It might be a little bit smaller than B. Because if n is perfectly divisible by B, then all the mini batches will be exactly the same size. But if not, the last one will be a little bit smaller, and that's just how it is. Okay, so that's basically how we've organized our training set into these mini batches. And then as we discussed in the last page, we're going to use one stochastic gradient descent iteration for each mini batch. And so that means after we go through T of those iterations, we will have processed each of our training samples once. And this number t, or t iterations, we call that a training epoch. And so basically at the end of the day, the algorithm is like this. You have an outer loop over epochs. And within that outer loop, you do two things. First, you randomly partition all your training indices into those t different mini batches. And then for each one of those mini batches, we compute the gradient and do one stochastic gradient descent update. So this is sort of like an inner loop here over t things, and then we have an outer loop where essentially we do random shuffling to get our subsets, and then we do run the inner loop. And typically you measure convergence or running time, let's say, in terms of how many epochs you run. So you say, like, I ran this for 10 epochs. I went through my training data 10 times. That's how people typically talk about it. You don't say, like, I ran this for 100,000 iterations. Sometimes people say that, but usually they tell you how many epochs it is, how many times they went through the data, because that's more interpretable. You don't have to know exactly how big your training data set was. You can just get a sense for how many times did you go through it. Okay, so that's the implementation. All right, any questions on that? Good, okay. So then we're gonna switch gears and talk about backpropagation. So again, coming back, we have now our stochastic gradient descent update. You can see we're taking the samples in the teeth mini batch, we're dividing by the size. We have the gradient of that thing. But that's the question now is, how exactly do we compute the gradient with respect to our parameters? And our parameters are, in this case of a two-layer neural network, we have the weights and biases of the hidden layer, and we have the weights and biases of the output layer. So how do we compute this gradient of this thing? So basically, we want to make this tractable, so we're going to start thinking about scalar calculus. Basically, look at the partial derivative with respect to each parameter in our set theta. So when we talk about this WH matrix, it's a matrix that has rows L and columns J. So I'm going to have to look at the gradient of my loss with respect to the Lth row and Jth column of this matrix. And then for this term, that's a vector. Maybe we'll index the vector by L, and we have to look at the partial derivative of that loss with respect to the Lth term in the vector. And then similar for the output parameters. So these are all the things we need to compute for a single stochastic gradient descent update. So that's what we're going to do next. It's a little bit complicated, but we're going to go in steps. And just to make the notation easier, we're going to omit the iteration index t, because we're going to do the same thing for every t, so it's not important to talk about t, really. We're going to focus on what happens in any given t. Okay, so that's where we're going. To understand things and visualize things, we're going to use something called the computation graph. And the computation graph is basically just a way to depict how the different parameters in our system depend on each other, or are So here we have, on one side, we have the loss. That's really the thing we care about taking the gradient of. And then we have our data, features, and labels. And then we have the current parameters, the ones we updated in the last iteration. And basically, we have all these, you could say, sort of like internal variables or derived variables. And this just happens to be what we have for the structure of our network. So for example, the hidden scores, the scores in the hidden layer, depend on the input features and the weights and biases for the hidden layer, right? So once you can compute those scores from those things, basically from this equation here. So if I tell you xi and I tell you the current parameters, you can compute the scores for that sample I. And now we're going to think of I as being an index within our mini batch of B. So we're going to have to basically do this operation for I equals 1 through B. And then we will know these numbers. Given these numbers, we know how to get the hidden layer activations by just putting those through the activation function. Maybe it's a sigmoid, maybe it's a ReLU, whatever it is, we know what it is. So given the ZHIs, we can compute the AHIs. So now we know those. And given those activations and given our output layer parameters, we can compute our output layer scores according to this equation. And finally, given those output layer scores and given our training labels, we can compute the loss like this, just by summing over that batch. Summing over the elements in the batch. And this process of starting with this stuff and making your way to the cost is known as the forward pass. So that's the first step in computing the gradients, is to figure out what are the values of all these things at the current iteration. Once we know those things, we can do a backwards pass, where we're going to start on the right side and we're going to make our way left by computing gradients one after another, building on previous computations to avoid redundancies. So that's what we're going to discuss in the next few slides. We're going to go slowly. Let me just point out one thing. You'll notice that I am not computing the activations in the output layer here, computing the scores and directly computing the loss based on the scores. But as we know, you could insert another line here. You could insert another node in the graph that has the outputs. It would just make things a little bit more complicated, and this is enough for us to describe all the ideas. Okay, so all right, are we good so far with? Okay, so then before we move on, let's talk again about the chain rule. And now we'll talk about it with the aid of a computation graph. So in this computation graph, you can see that Z depends on Y and Y depends on X. And so if I want to do something like dz dx, I can compute that from this product of dz dy times dy dx. Right? This is just calculus that you learned back in high school. Now, let's say that I have exactly the same graph, but I just happen to insert one additional node here. So one way I could do dz dx would be the same idea, dz du times du dy times dy dx. But actually, if you look at this computation here, dz du du dy is the same as dz dy. Right? So that means that you're allowed to skip over these nodes when doing the chain rule. You can just do dz dy dy dx. You can involve this if you want, but you don't have to. So that's going to help us a lot when we have this, big computation graph. We're going to be able to skip over things if we want. Okay. Any question on anything so far? Okay. And then let's also talk about what happens when there's a number of variables in one of these nodes. So another way to visualize this might be if we draw I could expand this into, okay, so what I'm saying here is there's like a set of variables yi. So another way to visualize that would be like the set of yi would be like those things. And so what we're saying is that you could also think of the computation graph going like this. So that means basically there's different ways the information between x and u flows. It flows through each of these different yi's in the set. And as a result, we have this multivariable chain rule that we talked about before. So if you want to do, dz dx, we could choose to involve u if we want, like I drew here, or we could choose to, just omit u and think of these, if we want, as directly connecting to z. And if we do that, that's what this expression over here says. So that says, now we're going to have a sum over those different paths, and we're going to have dz dyi, dyi dx, but we're going to have to sum over all the i's. Okay, so that's sort of different options we have with the chain rule. Any questions on this last one? Okay, so now that we have all that together, we can apply that to our neural network. But we're going to start with the simplest possible case where all the variables are scalars and the batch size is 1. So in reality, a number of these things are vectors or matrices, and we have a batch of size b that's greater than 1, but just for now, let's see what happens in the simplest case. Okay, so the first thing to do is the forward pass. So we're basically at the beginning of this iteration of stochastic gradient descent. We're given the old parameters. We're given batch size 1 training data. And the first thing to do is to compute all these derived variables all the way up to the loss. So here is the forward pass for this. We, given x and our parameters, we compute zh. Then given our activation function and zh, we can compute ah. And then given ah and our output parameters, we can compute zo. And given whatever loss we're working with, it might be cross entropy, it might be quadratic, but we know what it is. Given our label and our score, we can compute our final loss over the batch. So this is the forward pass. We do this first. And now these are all numbers for us. They're numbers that are stored in memory. Any questions on that part? Okay, so now the backward pass is more complicated, but we're going to start on the right and we're going to move our way left. So the way that I've organized it here is we're going to compute all the gradients along the top row, starting top right. So first thing we need to compute is dj dzo. So we can look up this equation, and I don't know the exact form of this because it really depends what we're dealing with, whether it's cross entropy or quadratic or whatever, but it's something we know, and it's something we can compute that derivative. So here I'm just calling this j prime. It's the derivative of j with respect to the first argument. So that's something we can compute. We know the value of zo, so we can plug that into the function, and we can actually store this as a number. Okay. So now that's the very first thing. We've computed this gradient. The next thing is to do dj dah. So we can do that, again, by the chain rule. That's dj dzo times dzo dah. This equation, right? And this is a number that we already computed. We don't need to recompute it. So this is just going to be, we're going to plug that in and multiply times a new number, which we do need to compute right now, dzo dah. To figure out what that is, we have to look at that corresponding step in the forward process. But now you can see that's pretty easy calculus. dzo dah is just nothing more than wo, right? And so that's a value. We know that value because it was given to us. And so we can basically do this multiplication, and now we have this as a number. Now we move on one step further in the reverse process. We compute dj dzh as dj dah times dah dzh, like here. And this first term, we just computed and stored, so that's going to be a number we have available. And then the only thing we have to figure out now is DAH, DZH. But for that, we just look up this line. And this activation function, I'm not sure which one we're using. It could be ReLU, it could be sigmoid, but we know what it is. We can differentiate it. So to compute this, it's just the derivative, I'll call it H prime evaluated ZH. And ZH is something we computed in the forward process, so that's something we know. Okay, so at this point, we've computed all these different derivatives. Any questions so far? Okay, so now we're going to get finally to what we're after, which is the quantities we need for our SGD update, like DJ, DBO. So for that, we could do DJ, DZO times DZO, DBO. So that's what we have down here. Now this DJ, DZO is something we already computed, so we know that. The only thing left now is to compute DZO, DBO. We just look over here, and we see that that derivative is 1. So that's easy. So now we know DJ, DBO. And so that's one of the things we need for our stochastic gradient descent update, in particular our update of the parameter BO. Now we can do DJ, DWO, same way. We again use this value over here, but now we just have to do DZO, DWO, which you can see from this equation is just going to be AH. Okay, so that's pretty easy. And then the last two are DJ, DBH, which we can do by DJ, DZH times DZH, DBH, like this. And we already computed this up here, so that's a number we know. And then this one over here, DZH, DBH, you can see is just going to be 1. Okay. And then the last one, very similar. So that's the basic process. So we started with the things we knew, ran the forward process to compute all these things, and then we worked our way backwards computing gradients, and finally we got gradients with respect to our parameters. Now we can go back, we can do the stochastic gradient descent update, and we get new parameters, and we repeat. Forward process, the backward process. Okay, so that's backpropagation. How's it going so far? Is it making sense? Okay, any questions on anything we've done? Okay, ready to move on to a slightly more complicated scenario where we have several values in our batch. Okay, so now I have a batch size of 1. So as a result, I put some curly braces here, meaning we have a set of scalar features xi. In particular, we have b of them. And we also have a set of training labels in our batch, b of them. These things, for now, are still scalars, weights and biases. So for the forward pass, we need to take what we know, and we need to compute these things sequentially. First, this one. So this is our equation. So we know for each of the i's, we can actually do this separately. We take that xi, multiply, scale and shift it to get zhi. So we can do this for all b values of I, and now we have those things. Then we can put all of those different hidden layer score quantities through our activation function, and we can compute these. We do that one at a time for each I. So now we know our hidden layer activations. Then from our hidden layer activations, we can use this equation to get our output layer scores. And finally, we can compute the cost for each of those elements in our batch and then sum them to get this final cost for the entire batch. Okay, so that's the forward pass. Any questions on the forward pass? Okay. All right, so the backward pass starts to get a little bit more interesting because we'll have to start thinking about the multivariable chain rule. In particular, we have to think about what is the nature of the multiplicity in this node? So if you kind of think carefully and look at the structure of the forward pass, you'll notice that there's actually a lot of decoupling across the different eyes. Meaning every sample in our batch xi will give a separate one of these and so on. So perhaps we could even draw it like this. We could imagine that there's some additional nodes there, and essentially there are parallel lines connecting them, right? They're decoupled. So this is what we have over the batch. But now when we think about how the different batch elements are interacting with the output layer parameters, you can see that, for example, B, O, and WO, they affect all the eyes, right? So that would mean that we would need to connect those like this. Similarly like this. And we also have several samples Y. Okay. So everybody good so far? Okay, so let's think about the things we'll need for the backward pass. So we're going to first do these different gradients. So DJ, DZO, I for all the different I. And so that's going to be, basically we just look at this equation. So if I do, maybe we should, like we've done elsewhere, is like put a prime on these I's. And then if I do DZ0 or DOI, there's only one term in the sum that matches, where I prime matches I, and so we basically just get a scalar quantity. Okay, so that explained what happened over here. This is why the sum vanished. Any questions on that? Okay. And then what about like DJ, DAHI for one of these? Well, you can see because of the decoupling, I can just look at that branch. Basically, I don't have to think about mixing across the different batch elements I. So really, there is no multivariable chain rule for this step. It's just like it was before. So DJ, DAHI for any I is DJ, DZOI for that same I times DZOI, DAHI, again for the same I. And just like before this one, we can look at that derivative for a fixed I, that's just going to be WO. And similar for these terms, so you could do this skip like this without really worrying about the different paths. They're all in parallel. Okay, so far, no multivariable chain rule to worry about. Is everybody okay with this part here? Okay, now let's think about DJ, DBO. So here, when I do DJ, DBO, I have to go through all those parallel paths, right? So that means I will have multivariable chain rule across those different I's, and so that's why we see the I sum here. But otherwise, if you look at just one term within that sum, it's identical to the last slide. It's DJ, DZOI times DZOI, DBO. And that we get from this equation. We can reuse those computations here. Okay, and then for DJ, DWO, it's basically the same. We have to consider all the different paths to WO. So we do have the multivariable chain rule there. And this other stuff is similar. So like to get DJ DBH, we have to consider all those paths. Like that. So we have the multivariable chain rule down here. Okay, so what questions do you have on this? Is it making sense, more or less? Okay. No questions? Okay, good. So now let's take it up a notch. So now we have multiple things in the batch, but those things are actually vectors. So now it's going to be a little bit more complicated. In terms of the forward pass, these are the equations. So let's just take a look at the first one here. Given feature vector xi, we have an entire weight matrix and bias vector that give us this vector z for that single I. So we do this separately for each I in our batch. You can see there is quite a bit of mixing. There is no decoupling unless this matrix is diagonal, which in general it's not going to be diagonal. For a fixed I, all these different elements are all mixed together. Now over here, there is decoupling, because if you remember that the way that these hidden activation functions work is that they work on scalar entries. So for example, your sigmoid is going to work individually on every sample within this vector, as well as being decoupled across batch items. So this one is decoupled, but these two things are not decoupled. In those ones, this matrix sort of mixes all the x's together to get z, and mixes all the a's together to get that z. So anyway, we do the forward process. We get all the quantities there. Any questions on anything in the forward process or the computation graph? Okay, so let's think about coming backwards. So this, we have these different paths, like before. But what we have in each case is we have a vector of parameters. So let's think about, okay, the first step doesn't really change. This step here. So we're going to want to look at, I don't know if I drew this well. Okay, so this might be, here I have like a vector of 3 parameters. So I want to compute dj dzoi, but for each one of the elements in that vector, and here I'm denoting those with the index k. So k is like as you go down there. So we have dj dzoi k for all the different k's and for all the different i's. So this is going to be, basically a matrix worth of computations. But we can compute all those quantities. Okay, then next, what about this? So over here, we have, again, a vector for each one of these. So here I want to do dj dahil. So I'm looking at one of these in particular, and I want to know how does the information flow from here to there. So you can see that there's this decoupling across the i's, which is nice. But if I think about the other variables, so I'm using, in this case, L. And I'm using L to index across the elements of the A vector. And I'm doing dj, let's say the first one of these, I actually have to go through all the different elements of this other vector. Right, so I'm gonna do multivariable chain rule across with a sum over k. And so that's why we have multivariable chain rule here. And then in terms of the derivatives we have to compute, d0 ik dah il, we need to look at this equation. So we can think of k as the variable that indexes down the z vector, and we can think of L as a variable that indexes down the a vector across the columns of this matrix. And so if I want to do d0 ik dahil, I'm looking at the lth row of the W matrix and the kth row and lth column of this matrix. So that's why it's going to be WOKL. Okay, so any questions so far? All right, it's more of the same of this, but like, I guess we're out of time for today. We can come back and start talking about this on Wednesday and answer any questions you might have. All right, see you guys then. Kyle?
For some reason, my computer was having issues, so I went to restart it, and it's been updating for like 30 minutes now. So
Okay, do you want me to post these notes?
I mean, no,
Together?
I'm fine because I was taking them on my iPad,
Okay.
but I was gonna use it to show you the lab. So I finished it yesterday, but I just wasn't sure. Like, I figured instead of just making you start an office hours call, I mean, the first thing I noticed was I was getting like sideways values, and I didn't know if I was supposed to input something to make it so they're like straight up and down. But that's the letters, and then above is the numbers. I mean, you can tell what they were, but it's just, I just wasn't sure if they were supposed to be flipped like that.
I feel like they shouldn't be flipped, but
Yeah, I mean, I think I went like mostly based off the demo to get those to show up, and I didn't know if I was missing like an access command or.
so this was directly from the demo, right? You didn't even have to change this?
Yeah, that was exact. Like,
Okay.
I mean, I think this was given to us. I
Yeah.
don't think I like had to copy it from the demo, which is why I was like a little confused at first. But I mean, it looks like I was getting the right values. It's just sideways. I think all of them are. Or I guess for some reason
Also,
some of them are
they're
like the
flipped.
one looks flipped fine, but
Because these are the numbers, right? Yeah, these are digits. So like the
Yeah.
3s are also flipped.
yeah, I'm not like I didn't know if I mean I could always come to office hours to fix that.
Yeah, I don't know offhand.
I'll see if anyone else
I would,
runs
yeah,
into that
you
issue.
could
when
post something to the discussion board,
Okay.
and then
I was gonna see
and then
if
like the
anyone-
TA would also probably be able to
yeah, and then
give a
I
hint, because
I
I'm not
guess-
sure what's happening.
think everything else